Welcome to our channel, and as always, thank you for tuning in. We've had a lot going on during the past few months. We were co-authors on two papers that were presented at DVCon 2024 on AMS and UVM. We released version 2 of Models in Minutes. We put together some case studies and testimonials that explains the Designer's Guide Advantage. Please visit our website to find out more. Besides many new capabilities in MIM version 2, including its ability to run standalone, we've made quality of life improvements to the user interface and added new features that enhance both MIM versions 1 and 2. Today I'll be demonstrating a new feature for both versions of MIM that we call Models in Seconds. Here's a spec sheet for a BIOS generator. If you watched our previous videos or are a customer, this should seem straightforward. We have a supply and ground, we have an enable pin, we have a voltage reference pin, which is an output of 1.25 volts. We have three arrays of current outputs, two P-types and one N-type. On the P-type, one array has 250 nanoamps and the other 500 nanoamps. We specify that the current should be pulled from VDDA for the P-types and that the current should go into ground for the N-types. We put ranges which will ultimately turn into assertions on the supply and ground. And we want to check that on the enable input, there's never an X. Using MIM version 2, from this example, we generate a Verilog AMS model that is over 400 lines long, a discrete electrical system Verilog model using user-defined types or UDTs that is roughly 250 lines long, and most importantly, a test bench that's roughly 870 lines long that when run verifies that the model and schematic are functionally equivalent. The generated models are fully featured. They contain the behavior, assertions, convenience features to simplify debugging, and are consistently generated so that all of your models will be in the same style and use the same coding conventions. So from an 8-row table, we generate over 1,500 lines of code. That's models in minutes. It's minutes because to enter what you see in this table probably would have taken someone on the order of 10 minutes to enter. But what if I were to tell you that this spec sheet that we just reviewed that generated these 1,500 lines of code was itself generated? No one typed in any of what you see here in the specification. This page was fully automatically generated. How did we perform this magic? We started with the symbol. For those unfamiliar with the analog flow, symbol creation is part of the analog design process. For every block that is designed, there is a symbol, and that symbol is what is instantiated in schematics along with the wires. Further, our observation has been that analog designers typically follow some type of naming convention for their pins. They are usually different between design groups and companies, but they do follow one. VDDA and ground A are common names for the analog supply and ground. EN for enable is very typical for the analog enable line, and even if they don't use EN, they use something for enable that is the same across all blocks. The same goes with the analog supply and ground. Then they name bias pins in such a way that you can tell if it's a voltage or current bias, and usually the value and type are encoded in the name. From this symbol and a customizable pin naming convention rules file, we generated the spec sheet. To see this in action, I created a new directory so that it's easier to see what's going on. Our AV utility, which is included with MIM, is used to convert a symbol to a MIM specification. I run AV convert with the location of cdslib along with the cadence library and the cell name of the symbol. This generates the bias specification in MIM text format. The information here is exactly the same as what we saw before on the web page. Here, for example, is the VREF output pin with its behavior, the N-type iBias output pin and its behavior, and here's VDDA with the range as specified as before. To generate the models and test bench, I'm going to use a standalone version of MIM. Running this is the equivalent of using generate and view on the MIM webpage. I type MIM, then the name of the .mim file that was just created from the symbol, and that's it. Now I have everything that I need for the model versus schematic simulation, including the AV settings file and generated connect modules. And in the local directory, I have the Verilog AMS model, the system Verilog model, the test bench, along with the other views such as config views for the cadence hierarchy editor. I'm now going to run the model versus schematic comparison. To make this comparison meaningful, I've purposely introduced an error in the schematic. For one current output, instead of producing 500 nanoamps, it produces 750 nanoamps. Now, all on one line. I'll publish the generated views into the cadence hierarchy, netlist, and run model versus schematic verification. We now see the error as expected. So it looks like on the second element of iBias 500N IBP, the schematic is producing 750 nanoamps instead of 500 nanoamps, which is exactly the error that I introduced on purpose. Finally, to complete this circle, if I want this spec sheet on the website after running the AV convert command, I can simply run AV initiate with the .mim file. In this case, I also specify the container into which I want the spec sheet to be placed. I'm not going to execute this command since this has already been run. The spec sheet that I showed at the beginning of the video is the result of running this command. This is models in seconds. We've gone from models in minutes, where we start with the specification, to models in seconds, where we start with the symbol. Here are a few parting thoughts. While it is obviously better that the input to the model creation process is something that the analog designer already creates, to be fair, the model engineer likely is already taking advantage of any pin naming convention by doing by hand what we're doing automatically here. However, with this automation, the pin names are now executable and are now being verified using the model versus schematic test bench that we create. How many hours have been wasted tracking down why a pin name will say one value when the schematic produces another? I've certainly wasted more hours than I care to remember on this. Of course, if you'd like to keep a pin inconsistency, that's up to you, and the specification can be edited to reflect this. You might be wondering, is this example too simple? Probably. This is what we can do now. In future videos, we'll be exploring more of what can be done by adding additional patterns to the rules file. The rules file is where time and thought is required. Second, our observation is that most pins on analog blocks are simple pins, such as bias inputs, trim bit settings, supply, and enable lines. So extracting the specification from the symbol can take care of many rows in a specification. And as such, even if we can't generate a specification fully, the specification that is generated serves as a great starting point, with many rows that are generated automatically. For those of you who are existing customers, thank you. And if you've been downloading and installing the latest version of AV, you already have access to this capability. Thank you for watching. Please click in the upper left for our next video. Please click in the lower left for the playlist of all of our videos in this series. Please click on the right to subscribe to our channel.